Here in Washington, we have our own volcano threat in the Cascade Mountains, which on average erupts once or twice every century.
Oregon and Washington have been identified by the U.S. Geological Survey as very high threat volcanoes.
USGS scientists monitoring the Cascadia subduction zone have just issued a red alert after a cutting-edge satellite system revealed what appears to be an extensive underground network of magma conduits stretching from Mount Meager in British Columbia deep into the volcanic fields of the Pacific Northwest. The imagery, captured by a next-generation interferometric radar satellite, shows subtle but coherent ground deformation patterns aligned along trajectories that connect one of Canada's most restless volcanoes to a string of active peaks in Washington and Oregon. This discovery has sent shockwaves through the volcanology community because it suggests that, far from being isolated plumbing systems, the magma reservoirs feeding these volcanoes may be part of a far more integrated magmatic complex than previously imagined. Before we start, hit the like and subscribe buttons for more exclusive news. When the first hints of this subterranean corridor emerged, researchers were naturally skeptical. Mount Meager, situated within the Garibaldi volcanic belt, has been recognized for centuries as a potential hazard. But its magma chamber was thought to lie in isolation, fed by local melting of the subducting Juan de Fuca plate. Likewise, the Cascade volcanoes, Rainier, St. Helens, Hood, and their neighbors, have each been studied as distinct entities, with unique magma chemistry, eruptive histories, and seismic signals. The new satellite data, however, paints a more interconnected picture. Ground tilt and swelling indicators that move in concert across staggering distances, hinting at deep channels where molten rock can flow from one reservoir to another. The implications of such an interconnected system are profound. If magma can traverse these tunnels, pressure changes in one chamber. For example, a sudden influx of melt beneath Mount Meager could transmit stress pulses to the Cascade volcanoes, potentially hastening an eruption day of one of the most densely monitored volcanic peaks in North America. Conversely, activity beneath Rainier or St. Helens could influence conditions at Mount Meager, a volcano that, despite its history of violent debris flows, receives far less attention and fewer resources for real-time monitoring. This asymmetry in surveillance could leave a critical blind spot in continental volcanic hazard assessment. At the heart of this revelation is a sophisticated technique called persistent scatterer interferometry. By analyzing millimeter-scale changes in the Earth's surface over time, the USGS team detected a sequence of uplift and subsidence events that, when mapped in 3 dimensions, form a web of subterranean pathways. These observations were corroborated by a network of GPS stations on either side of the international border, which registered synchronous movement in ground positions. Geophysicists emphasize that while such data cannot directly image molten rock, the deformation patterns match simulations of pressure-driven magma flow through rigid crustal fractures, akin to the way blood travels through veins. In practical terms, the presence of these conduits could mean that magma destined for one volcano might be diverted or shared with another. This phenomenon, while well established on much smaller scales beneath individual volcanoes, has never before been documented at intervolcano distances of tens to hundreds of kilometers. If confirmed, it would demand a re-evaluation of eruption forecasting models, which currently treat each volcano largely independently. Hazard maps, emergency response plans, and public warnings would all need to account for the possibility that an uptick in seismic tremors at Mount Meager could foreshadow unrest at Mount Hood or Mount St. Helens days or even weeks later. Perhaps most unsettling is the idea that such a molten network could facilitate the transfer of chemically distinct magmas between systems. Laboratory analysis of gas compositions venting from fissures near Mount Meager has already revealed anomalous helium ratios inconsistent with local basalts, suggesting an influx of deeper, mantle-derived magma. Should this mantle magma migrate through the tunnels, it could recharge the Cascade reservoirs, altering the physical properties of the resident magma, its viscosity, volatile content, and eruptive style. A volcano primed with fresh gas-rich magma is more likely to produce explosive eruptions, as trapped volatiles rapidly exsolve when pressure decreases near the surface. Beyond eruption risks, the discovery raises questions about long-term volcanic evolution in the Pacific Northwest. Geochronological studies of lava flows and tephra layers have shown episodic pulses of volcanic activity across the region over the past million years. Some researchers now speculate that these pulses might correspond to times when the magma network was more active or when tectonic stresses opened new channels. The newly detected tunnels could be the modern remnants of a grand subterranean highway that has periodically reignited volcanic belts, shaping the landscape through cycles of eruption and collapse. Communities living in the shadows of these mountains may soon face a more complex threat matrix. Cities like Vancouver, Seattle, and Portland have robust emergency management systems geared toward major volcanic crises, primarily focused on localized ashfall, lahars, and pyroclastic flows. Yet they may now have to prepare for a scenario in which multiple volcanoes erupt in quick succession, or even simultaneously. Such an event would compound hazards, as overlapping ash clouds could disrupt air travel across the continent, while cascading lahars could clog river systems on both sides of the border. Scientists caution that there is no immediate cause for panic. The red alert issued by the USGS Volcano Hazards Program signifies a state of heightened watchfulness rather than an imminent eruption warning. The agency has raised the volcano alert level from normal to advisory for both Mount Meager and several Cascade peaks, meaning that observers will increase the frequency of satellite overpasses, seismic monitoring, and gas measurements. Field crews are already redeploying to install additional infrasound sensors and long-period seismometers along the suspected tunnel axis, hoping to catch any precursory signs of magma migration in real time. At the same time, academic institutions and research consortia are mobilizing to conduct magnetotelluric surveys that can constrain the electrical conductivity of the crust, another proxy for fluid pathways. If the tunnels contain partially molten rock or hydrothermally altered zones, they will appear as conductors against the surrounding bedrock. Integration of these data with the deformation maps could yield three-dimensional models of the network's geometry, depth, and connectivity strength. Such models are essential for assessing whether magma movement is confined to deep levels or if it penetrates all the way to shallow reservoirs beneath the volcano's summits. Insurance companies are already reviewing their risk portfolios. In the Pacific Northwest, many policies covering volcanic damage hinge on models that assume independent volcano behavior. A connected system could invalidate these assumptions, exposing insurers to correlated losses across multiple regions. Reinsurance firms are particularly attentive, as simultaneous claims from Canada and the United States could dwarf the financial impact expected from a single volcano event. Some analysts predict a recalibration of premium rates for critical infrastructure located near these peaks, including hydroelectric dams, major highways, and airports. The geopolitical dimension of this discovery is significant. The transboundary nature of the magma tunnels necessitates cooperation between the USGS and the Geological Survey of Canada. While both agencies have a history of collaborative research, the stakes are now higher. Protocols for data sharing, joint exercises, and cross-border evacuation drills are under review. National defense departments, too, are taking notice. Volcanic ash clouds can interfere with satellite communications and radar, affecting military readiness. Consequently, strategic coordination is being discussed at ministerial levels in Ottawa and Washington. Tourism operators and outdoor enthusiasts will also have to adapt. The Pacific Crest Trail and ski resorts on Mount Hood, for example, might face temporary closures during periods of increased unrest, even if no eruption occurs there directly. Adventure travel companies are revising their contingency plans, including early warning notifications and rapid evacuation routes. Conversely, some see an opportunity for citizen science. Hikers equipped with smartphone apps could report unusual rockfalls, sulfur odors, or subtle ground rumbling, supplementing formal monitoring networks. This event also resonates with a broader scientific quest to understand how magma moves within continents. Previous paradigms emphasized isolated magma chambers, bubbles of molten rock that evolve in place until they erupt or solidify. The new paradigm, suggested by these magma tunnels, imagines a vast dynamic circulatory system beneath active volcanic arcs. It has parallels in Iceland, where interconnected fissure systems feed multiple vents, and in Indonesia, where lava tunnels link adjacent volcanoes. Yet the Cascadia network, if confirmed, would be unprecedented in scale, running along a subduction-driven arc that spans international boundaries. Cultural and indigenous perspectives add another layer to the story. First Nations and Native American tribes in the region have long oral traditions about the spirit and power of these mountains. Some legends speak of fire rivers beneath the earth that connect distant peaks, a poetic echo of what modern science may now be witnessing. Tribal councils are engaging with volcanologists to integrate traditional knowledge about land changes and sacred sites into hazard planning. Such collaborations aim to ensure that risk communication is culturally sensitive and that evacuation protocols respect ancestral territories. On a more philosophical note, this discovery reminds us of the planet's restless nature. The ground beneath our feet, which seems stable and unchanging, hides forces that operate on timescales and scales beyond human perception. The magma tunnels beneath Mount Meager and the Cascade volcanoes serve as a potent metaphor for connectivity, how separate systems can be linked by hidden channels, and how changes in one corner of the world can reverberate far away. In an era when we increasingly face interconnected challenges, from climate change to pandemics, the Earth's own underbelly offers a stark illustration of interdependence. One of the most pressing questions is whether these tunnels are permanent features of the crust or transient structures that open and close in response to tectonic stresses. Computer models suggest that fracture networks can heal as magma cools and mineralizes the fractures, sealing pathways until renewed pressure reopens them. If the Meager tunnels are ephemeral, they might explain why periods of widespread volcanic activity have occurred sporadically in Earth's history. Conversely, persistent channels could maintain a baseline of magmatic interaction that continuously shapes volcanic behavior. Meanwhile, efforts to improve real-time monitoring are accelerating. The USGS is fast-tracking the deployment of portable magnetometers, Doppler radar installations for ash plume tracking, and drone surveys equipped with thermal cameras. Satellite operators are reprogramming tasking schedules to prioritize passes over suspected tunnel sites, allowing interferometric images to be generated every few days rather than weeks. The goal is to create a living, three-dimensional map of pressure changes and fluid movements in the crust, a revolutionary advance in volcanology. As the red alert status holds steady, scientists caution that much remains unknown about these magma tunnels. Confirming their existence and understanding their dynamics will require a concerted effort combining fieldwork, remote sensing, laboratory experiments, and theoretical modeling. Yet even at this early stage, the discovery has already upended long-standing assumptions and opened new avenues of research. It serves as a vivid reminder that the Earth is an evolving system, full of surprises that can transform our understanding of the world and our place within it. Beyond the immediate hazards, the revelation of a sprawling magma network beneath the Pacific Northwest invites a reimagining of geothermal energy prospects. Regions once deemed marginal for high-grade heat extraction could now be reconsidered. If conduits channel magma closer to the surface in discrete pockets, those hotspots might offer renewable power sources capable of supplying communities with carbon-free electricity. Exploration teams are already evaluating deep exploratory drilling to map temperature gradients along the suspected tunnel corridors. Advanced logging tools, such as fiber optic distributed temperature sensing, would allow precise, continuous monitoring of heat flux, revealing whether these subsurface arteries could sustain long-term energy production without triggering undue seismicity or inducing unintended pressure perturbations. In tandem with energy research, the discovery has galvanized efforts to refine regional climate models. A multi-volcano eruption scenario could inject vast quantities of sulfur dioxide and ash into the stratosphere, momentarily cooling global temperatures. Past events, like the eruption of Mount Pinatubo in 1991, demonstrated how a single eruption can lower average temperatures by nearly half a degree Celsius for a year. Now, scientists must contemplate what simultaneous or sequential eruptions of multiple Cascade volcanoes might do. Would the cumulative aerosol loading amplify cooling effects, or would interacting plumes dilute each other's radiative impact? Sophisticated atmospheric simulations are being developed to capture these nuances, feeding into seasonal and decadal climate forecasts that could inform agricultural planning and water resource management throughout North America. Meanwhile, public health experts are poring over historical data on volcanic particulates and respiratory illness. Mount St. Helens' 1980 eruption, for instance, correlated with spikes in hospital admissions for asthma and chronic obstructive pulmonary disease in downwind communities. With the potential for overlapping ash events, the frequency and intensity of respiratory hazards could rise dramatically. Health departments are updating preparedness plans, stockpiling N95 respirators, and drafting guidelines for vulnerable populations, including children and the elderly. Telemedicine networks are being bolstered to provide remote consultations during ashfall emergencies, and air quality monitoring stations are being strategically placed along likely plume trajectories to deliver real-time hazard alerts. Ecological systems are also likely to feel the impacts of renewed volcanic activity. Salmon runs on key rivers such as the Skagit and Willamette could be disrupted by ash settling in spawning grounds, altering pH levels and reducing oxygen availability. Forest ecosystems that rely on gradual mineral-rich soil development might instead be coated in fresh tephra, leading to tree mortality in monoculture plantations, but perhaps fostering biodiversity in mixed forest stands where pioneer species can quickly colonize. Biologists are designing field studies to assess pre-eruption baseline conditions, enabling them to quantify ecosystem resilience and successional pathways once ash and pyroclastic debris settle. On the technological front, the magma tunnels have sparked a surge in novel sensor development. Researchers are prototyping self-powered seismic nodes that harvest energy from ground vibrations, eliminating the need for fragile batteries and wired connections. These nodes can be scattered densely across volcanic slopes to capture low-magnitude tremors and high-frequency fracturing signals, improving the granularity of eruption precursors. Simultaneously, efforts to miniaturize gas analyzers have produced portable devices capable of in situ detection of volcanic gases like sulfur dioxide and carbon dioxide with parts per billion sensitivity. By deploying these instruments in shallow fissures along the tunnel axis, volcanologists hope to trace subtle shifts in gas ratios that could betray magma migration long before surface deformation becomes evident. In academic circles, the magma tunnel discovery is already influencing geology curricula. Universities are updating courses on igneous petrology to include modules on interconnected magmatic systems, emphasizing field methods suited to mapping subsurface networks. Graduate students are vying for positions on research cruises that will sample offshore sediments in the Cascadia Basin for volcanic ash layers, seeking to reconstruct past episodes of linked eruptions. Collaborative workshops are convening experts in structural geology, geochemistry, and computational modeling to forge interdisciplinary approaches. Funding agencies, impressed by the broad significance of the finding, are offering multi-year grants to teams proposing integrated studies that span from molecule-scale experiments to continent-scale hazard analysis. Amid the flurry of scientific activity, policymakers are grappling with the need to update land use regulations near volcanic zones. Current zoning maps often demarcate hazard areas based on historical lava flow paths and lahar inundation zones, but they rarely consider the fluid dynamics of magma migration. Now, planners in British Columbia, Washington, and Oregon are assessing how to codify buffer zones around identified tunnel corridors, limiting certain types of development, such as high-occupancy housing or critical infrastructure, in areas that could experience unexpected uplift or ground cracking. These conversations extend to indigenous land rights, as many of the targeted buffer regions overlap with treaty-protected territories. Negotiations aim to balance safety concerns with respect for sovereign stewardship and traditional land uses. From a psychological viewpoint, the knowledge of hidden magma highways can influence public perception of volcanic risk. Past research indicates that familiarity with local volcanoes can engender complacency, whereas awareness of complex underground connections may heighten anxiety. Emergency managers are therefore consulting behavioral scientists to craft communication strategies that inform without alarming. Messaging focuses on practical preparedness steps, such as having emergency kits, evacuation plans, and communication protocols, while emphasizing the rarity of major eruptions. Community outreach programs are evolving to include virtual reality simulations, allowing residents to visualize potential eruption scenarios across multiple peaks. reinforcing situational understanding and fostering collective readiness. Meanwhile, artistic and cultural communities are interpreting the magma tunnels through creative expression. Poets write of subterranean rivers of fire that echo the interwoven dance of tectonic plates, while visual artists sculpt installations that mimic fractal branching patterns, evoking both beauty and danger. Museums are planning exhibits combining interactive geophysical displays, live feeds from volcano webcams, and indigenous storytelling sessions. These interdisciplinary installations aim to bridge scientific knowledge with human experience, inviting audiences to reflect on the interconnectivity of Earth systems and the communities that depend on them. In the realm of defense and aerospace, the tunnels pose both a challenge and an opportunity. Military strategists have long considered volcanic ash a hazard to jet engines and satellite sensors. The prospect of multi-volcano eruptions raises the stakes for aviation safety and reconnaissance capabilities. Consequently, defense contractors are exploring hardened sensor arrays that can operate in high ash concentrations, and drone platforms with improved filtration systems for sampling volcanic plumes. At the same time, climate scientists within space agencies are interested in how ash and aerosol patterns influence satellite radiometry, refining algorithms to distinguish volcanic particulates from other atmospheric constituents. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on magma tunnels? Will Mount Meager trigger eruptions in US volcanoes? We want to hear from you. Thank you for watching and see you next time.